So in continuation with our discussion on mathematical induction, the example 5 is prove that 1 plus x to the power n is greater than or equal to 1 plus nx for all natural number n. And please understand, x has to be greater than or equal to minus 1, and each and every line or word which is given in the question, this will be used. So let Pn be the given statement, as we always do. Pn is nothing but 1 plus x to the power n is greater than or equal to 1 plus nx for all x greater than minus 1. And we know that Pn is true when n equal to n. How? Let us place 1 here, 1 here. So 1 plus x is greater than or equal to 1 plus x. Actually, it is not greater than or equal to, it is exactly equal to 1 plus x. Now this is done. We assume that 1 plus x to the power k is greater than or equal to 1 plus kx. We think and we assume that this is true for some k. We are placing k here. Now we want to prove it is true for k plus 1. Okay. Before going to this, let us consider an identity. This has nothing to do with this question, but we are going to use this result. How? What is 1 plus x to the power k plus 1? We know that a to the power m plus n is a to the power m a to the power n. We know that. So what we are going to do, 1 plus x to the power k plus 1 can be written as 1 plus x to the power k and 1 plus x. And for this condition, when x is greater than minus 1, we know that 1 plus x will always be greater than 0. Please understand this identity we have used, and we know that for x greater than minus 1, 1 plus x will be greater than 0. Or what you can do, x is greater than minus 1, take 1 here. So it will be 1 plus x greater than 0. Now, this is what we have to, this is what we are given actually. This is what we are given. We are writing here now k plus 1. What this k plus 1 is, we are multiplying both the sides by 1 plus x and 1 plus x. Both the sides. So here we get 1 plus x to the power k plus 1 because we have multiplied 1 plus x both the sides. Here also 1 plus kx, we have multiplied 1 plus x both the sides. So we just multiply inside. Okay, we multiply it. We get 1 plus x plus kx square. Now, if at all we get rid of one member here, we can get this for k plus 1 also. How? Again, we'll use one more identity. Okay, k is a natural number. K is a natural number, and we know that x square is always greater than or equal to 0. Any number which is squared cannot be negative. So if we multiply k with x square, because k is a natural number, this will always be greater than or equal to 0. Say k is 2 and x square is say 3 square. This will always be greater than 0. So even if I multiply 2 with this 3 square, 2 into 3 square, this will also be greater than or equal to 0. So for k, for any natural number, k is any natural number, and we say that x square is greater than or equal to 0, kx square has to be equal to greater than or equal to 0, right? So what we are going to do is, this 1 plus x plus kx or 1 plus x plus kx, if we add this term kx square, this added term will make this greater than this. So now 1 plus x plus kx square is greater than 1 plus x plus kx by this discussion. So what we obtain here what we obtain here is 1 plus x k to the power 1 will be greater than or equal to this, and we have just proved that it is greater than or equal to this. So this you can write here. What you can do here is take x common. 1 plus k x. So the statement 2 is established. Thus, by the principle of mathematical induction, Pn is true for all natural numbers. Okay, we'll take the next one now. The next one is we have to prove that 2.7 to the power n plus 3.5 to the power n minus 5 is divisible by 24. So let us give this statement as Pn. We say that statement is this is divisible by 24. Let us check it for n equal to 1. Place n equal to 1 here. What do you find? You find that it is 24. So this is actually divisible by 24. So no problem with n equal to 1. We assume it is to be true for pk, means for k, for n equal to k, it is true. So this has to be some multiple of 24, say some q we take. Q belongs to this natural number. This is the but this is divisible by 24, so we can write it in the equation form as 24q. We have to prove for pk plus 1. What we do here, please understand it very carefully. This one we take 7k, 7 to the power k plus 1 is 7 to the power k into 7. Here also 5 to the power k plus 1 is 5 to the power k, 5 to the power 1. And in this case, this, just take 7 here, okay, take 7 common, and inside this you are left with 2 dot 7 to the power k. What I am trying to do here is, see, I am trying to add this value. I am trying to add this value, means we'll add this value and we'll subtract, because if I am adding we have to subtract also, because this was nowhere. We are trying to make it 24q, okay. So now this is added, this is subtracted, and again if this is added we have to subtract this, if this is subtracted we have to add this. This value we have written like this, left, or this we have just left, okay, we'll deal it with later. From this point to this point we are aware that this is 24q, and what about this? We are not aware. Let us multiply it inside by 7, 7, 7. So that will be 7 into 24q. This we have already got 24. Now this will be 21 5 to the power k. This will be 35. 7 5 is 35, and this we are left with. Combine these two terms. Combine these two terms. So this will be 6 into 5 to the power k, and 35 minus 5 is 30. We take 6 common here. 5 to the power k minus 5, and we are aware that 5 to the power k minus 5 is always a multiple of 4. Just take any value. 5, say k, we take 2. So 5 square is 25 minus 5, which will be equal to 20, and this is multiplied by 4. So this can be written as 4p. Why I am doing this? Because I want 24 somewhere here. So this I have done using this observation. So this is 6 4 24, 24p. Now 24 here, take 24 common. This can be any value. Just name it as r. So 24, and now 24 has come. So this is actually a multiple, or 24. This is divisible by 24. So this is how we come to the conclusion that if pk is true, pk plus 1 is true. Next is 1 square plus 2 square to n square is greater than n cube by 3. So Pn is this expression. Let us check it for n equal to 1. N equal to 1, place 1 here, place 1 here. So 1 greater than 1 by 3. Okay, this is true. Okay, this is true, no problem. 1 is always greater than 1 by 3rd. Let us assume it to be true for k. So 1 plus 2 square dot 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 k square is greater than k cube by 3. This we have assumed. We have to please observe this. First one we are going to use it later. Now let us see for k plus 1. So this we already know. Let us add k plus 1 also. So as we add k plus 1, this can be written as k cube by 3 from the previous expression. So k cube by 3 plus k plus 1 whole square. Let us rearrange it. When we rearrange it, we find that 1 by 3 k1 plus whole cube plus 3k plus 2. This term, as you see here, this term, they both are equal, but as we are adding this 3k plus 2, this is an added effect. So this particular whole expression will be greater than this, because this is the added term. This will add some extra amount to this. So by this we can prove that for every k, this is greater than this value is greater than 1 by 3k plus 1 whole cube. So pk plus 1 also holds. Let us prove the rule of exponent. So a b to the power n is equal to a to the power n b to the power n, and we use mathematical induction here. Pn is actually a b to the power n, a to the power n, b to the power n. Place n equal to 1 for our basic step. A b to the power n, 1 is a to the power 1, b to the power 1, so ab equal to ab. No problem here. Let us assume it to be true for pk. So ab to the power k is ak bk, right? This we have assumed. What about k plus 1? ab to the power k plus 1. What about this? This can be written as ab to the power k and ab. You know that a to the power m plus n is a to the power m, a to the power n. So what will this be? A to the power k, b to the power k. We know about this. This remain ab. Combine ak with a and bk with b. ak with a, bk with b. So this will be what? A to the power k plus 1, b to the power k plus 1. So for any ab to the power k plus 1, we get a to the power k plus 1, b to the power k plus 1, and we found that for every pk being true, pk plus 1 is also true. So by principle of mathematical induction, this is also true. So let us summarize that our basis of mathematical thinking is always deductive. Say A is greater than B, B is greater than C, you say A is greater than C. This is deductive reasoning. But we have found another way, which is called the inductive reasoning. That is, we say that we have number from say 1 to n. Just take an example. If it is true for 1, we take any value k. If we can find out that it is true for k plus 1, then we again can induct this, that is, it is k plus 1, we take k plus 1, it will be true for k plus 2, and likewise till n. So this is the inductive reasoning. For that, what we do, we choose this Pn, check it for correctness for n equal to 1. If it is true, then we go for Pk, we assume Pk, that Pk is true, and we try to find out or establish that Pk plus 1 is true. If for every Pk, Pk plus 1 is true, that means this expression or series is having the general solution. Okay, so this was all about mathematical induction. Thank you so much. Take care of yourself.